Right, let's have a wee look through this 2019 3A paper. The question 1 I don't think was that hard. You might disagree, but basically it was 3 springs all connected in series with each other, and then various masses were hung off the end and it oscillated and you had to time it. Again, in the actual exam you would need to make sure you're reading through all this information properly, because it will, just like this is unfamiliar to you now, it will be an unfamiliar equation to you in the exam. So you need to make sure you know what all the letters stand for and what they mean by different things. So if you were doing this, you had been told to measure, to attach a 100-gram mass hanger to the bottom here, and then measure the length of the spring system. So it's obviously going to have extended a little bit. Then basically you're being asked to oscillate it, so displace and release the mass so that it oscillates vertically with a small amplitude. In other words, don't set it going crazy or anything. Take readings to allow you to determine an accurate value of the period of oscillation, and record anything that you need to do in this table here. Now, obviously I had provided you with these numbers. So this was from these numbers I got from one of the pupils in the year above you. I hope they are decent results. You will know better than me. So there's 4 marks. Whenever I'm marking yours, I will have a wee list of ticks, probably, hopefully no X's. But this is the order that they will correlate to. So the first one will be this one here. There's 1 mark for having a heading which includes a suitable number of oscillations, and the way they determine that is if your times are all over 5 seconds. Now, because I have given you these times, everyone should be getting that mark. The reason that they might is if you've forgotten to put a unit on, and remember you have to use the slash for the unit, you can't use brackets. If you haven't said time for 10 oscillations, if you've just written time or something, I would take that mark off you, because that's not the time period. We were timed for 10, and I had everything that's written in this black pen here, that was in the picture I give you. The pencil I have written in since. Second mark, again, everyone should have, because again I wrote this for you. So the lengths all to the nearest millimeter and increasing, because obviously if they're not, you've done something wrong, you haven't followed their instructions. The third mark is for having 5 sets of readings with repetition for each length. Again, I've given you that, so we should have that mark. All to 2 decimal places. Again, we should have that. And then the last mark is for calculating the time period properly. So if you've forgotten to divide by 10, that would be the biggest common mistake there. Or not giving it to 2 decimal places will make you lose that mark as well. Okay, so after you had taken all your readings, then it's all the theory stuff. And they give you the equation here that you have to use. So T equals 2 pi root L minus L naught over P. It tells you that P and L naught are constants. Then asks, show that a graph of T squared against L will result in a straight line from which the values of the constants P and L naught can be determined. So this is what the mark scheme says, which I know many of you have already looked at. So there's 1 mark for correctly squaring both sides of the equation. I'm going to work through this now. There's 1 mark then for correctly expanding the equation, and then there's 1 mark for having it correctly mapped to y equals mx plus c. So even if you have expanded wrong, you can still get that 3rd mark. Okay. So if we look here, this equation is T equals 2 pi root L minus L naught over P. And because we have to get T squared against L, that means we need to get T squared to be the equivalent of y, and y equals mx plus c, and L is x. And we need to be able to find P and L naught. So one of these is going to be something to do with the gradient, and one of them is going to be something to do with the y-intercept. So the first thing, and suppose this squared is a wee hint for this, the first thing to do is to get rid of this square root. So to square both sides. So T squared equals 4 pi multiplied by L minus L naught over P. And then all we have to do is multiply out this bracket. So T squared equals, if you think back to like junior maths, L minus L naught over P is the same as L over P minus L naught over P. So 4 pi multiplied by L over P minus 4 pi L naught over P. Now I've kind of done two steps there at once because I was running out of room, but you could have had a step in between there where they were all 1 over the 1 and then separated them out. Then you can relate this to y equals mx plus c. So because we are plotting L on the x-axis, that is there. So t squared is 4 pi over p multiplied by L minus 4 pi L naught over p. We'll look at the mess of this I'm having to write on top of my own writing. So y equals mx plus c. Here we go. That's a mess, sorry. Hopefully you can follow what I was doing though. Part C. To draw the graph is necessary to calculate additional quantities from your results. 2 marks for filling in the final blank column of the table with an appropriate heading and values, and you needed to give them to 2 decimal places. So the heading is t squared and the unit is second squared, 1 mark for that, and then 1 mark for your t squared values being correct to 2 decimal places. You hopefully by now are familiar with what the marks are for in graph questions, although a bunch of you are still not spreading out your points far enough. So this next part is to plot the graph of t squared against L on the grid. 1 for your scales being correct, and this, what I've written here, means that your points have to take up at least half the space available. It's not just your scale, it's your points, and that's a mark that a bunch of you are still losing quite often. Label and units on axes, consistent with the table, so if you'd messed this up earlier on, as long as that's consistent, you can still get that. 2 for your points, and they take a mark off for each one that you get wrong, and then 1 for your best fit line. If you did your axes the wrong way around, you would lose 1 of those marks even if everything else was right. Oh. Okay, part 3, so nice and straightforward, calculate the gradient. 3 marks, 1 mark, a large triangle. Remember that means one of the bits of the triangle has to be 5 centimeters. Just use as big a triangle as you can, and points correct. Don't just pick a point from the table. It has to be a point on the line where it's on a nice little grid crossing. Then 1 for correctly calculating your gradient from your values, and then this is where they're really testing how good you were at the actual practical. So the quality mark here, your value unrounded had to be between 3.80 and 4.20. So even if you got like 4.24, which rounds to 4.2, they wouldn't give it that. Would they give that? I don't think they would. That was a bad example. What was a better one? What if it was 4.205 there? That's a better example. That wouldn't get that mark. Okay, part 4, use the value of the gradient of from part 3 to obtain a value for the constant p and include appropriate unit for p. So 1 mark for calculating your value from whatever you had up here, and the units are meters per second squared. So the units of p are going to be 1 over the units of your gradient. So because your graph was t squared against length, that means the units of the gradient are going to be second squared divided by meters. And because p, the units of it are going to be the inverse of that, so it's going to be 1 over it, that's where we get meters per second squared. Because if we turn that upside down, you get meters per second squared. Then D, what does the intercept of your graph with the L axis represent? These are the different ways they would have accepted your answer. It was on that very first page L naught was marked on. So you could say it was the unstretched or the natural length or the length when no mass was added. Finally, they did allow this L naught because that was defined earlier on in the question. What they did not accept is if you said the length whenever there's no oscillation, because if you think about it, if you put masses on that and it's stretched out and it's not oscillating, it's still not going to have the length L naught. Now question 2 you probably will have found a little bit more difficult because it is about capacitors and we have not learnt about that yet. You will learn about that with Mr. Ross next year. But if I can do it, you can do it. Okay, so the experimental techniques and all that, all the data analysis is all the same, and I think it gives you enough information in the question here about the equations that you have to use and things like that, that you can still do it even if you don't really know anything about capacitors. Okay, that's what I mean by if I can do it, you can do it. I know very little about them. So this circuit was already set up for you, and then it just told you what readings to take. So again, I know I'm flying through the instructions here, but I would not recommend that for real experiments. Again, tells you what to do here, and then results had to be recorded in the table. So basically it's really timing how long it takes the capacitor to discharge. It told you to take a series of current readings, 20-second intervals for 120 seconds or 2 minutes. So the results of that are there. I had given you those numbers, so everyone should have those 2 marks. Then you had to do your graph. I have not drawn mine yet. I tend to draw these as I am about to mark them. But 5 marks, and same as normal really for what the marks are for. This one should look like an exponential decay curve. So it should be an exponential decay curve. So here's what the marks are for, and again you'll get a list of marks. One for your scales, points taking up at least half the space available. I'm like a broken record. One for having your axes labelled correctly with units and consistent with your table. 2 for your points, -1 for each mistake, and then 1 for a smooth curve. Now, they are definitely fussier about your smooth curve here than they would have been at GCSE. At GCSE, really, you can get away with a pretty rubbish curve. Okay. Now, here were the examiner notes. Be reasonable. So, examiners marking this, they're not being too harsh, but they absolutely will take a mark off you if you have multi-lines. So 1 pencil stroke. If you have that, and then one wee section where there's another wee line, they're going to take the mark off you, okay? And absolutely, of course, not straight lines done like a dot to dot, so there should be no ruler in sight for this one. Okay, for part 3 here, it tells you really the rule that by the stage you'd be doing this at the end of next year, you would know this rule already, but it tells you it anyway. Now, here's my disclaimer. See this little symbol here? I've always pronounced it TAU. It's T-A-U. I'll write that in actually for you. Mr. Ross and Mrs. Turner both pronounce it differently than me. I promise other people in the world pronounce it the same way as me. I'm fully prepared to be wrong. But you know how hard it is to change how you pronounce things. So I think they say tau, something like that. I say taw. They make fun of me for it. We all move on. Okay. So the time constant tau is equal to the time taken for the current to reduce to 37% of its initial value. From your graph, you had to find a reliable in bold value for the time constant tau and record the value. So you have a wee graph of current against time, and it's roughly something like that. So wherever your initial current value is, then you would go to what 37% of that was and read off how long that took. Okay. And then, because it says reliable, you had to do that again. So find the second one, so 37% again of that. Get that time, and then find the average of those two. Okay. So there's 1 mark for finding 37% of the current, first of all. There's 1 mark then for then identifying that the time that took as tau/tau. There's 1 mark for the second tau being determined to make it reliable, and then 1 for you calculating an average. So there's a couple of different alternatives here. Some pupils, whenever they're doing this, would have just done 2 and divided by 2. That still only counts as 1 reading. It's not improving the reliability of it, so they would only have got those first 2 marks. Some people forget about the 37 and sort of think in terms of like half-life, if you remember that from radioactivity, and accidentally do 50%, and then some people do 63% because they read this as reduced by 37%, not reduced to 37%, so they would only get the last 2 marks. Now, for part 4, the time constant tau equals the product of the resistance R and capacitance C. So that means we can write that equation, which means that if you have a value here, then you can go on ahead and calculate the capacitance, because I'm pretty sure they give you the value of the resistor. Let me just check that. Yeah, they did. So right back at the very start, pardon me, of the question, it told you the value of the resistor there, so 33 kilo ohms. So 33,000 ohms is what you're putting in there to that equation for the resistance. So whatever value you had for your tau is equal to 33,000 multiplied by the capacitance, and then you can easily solve that for C. Okay, so for part B, there's further instructions, and again, they maybe don't mean that much to you now. Maybe the technology people, but the instructions maybe don't mean that much to you for now, but you can still do the practically type start parts of this question. Same again here, further instructions on what to do and different measurements to take, and this time, because basically in this time it discharges much quicker, it is getting you to take current readings every 10 seconds just for 60 seconds, and you had to fill in this table. 1 mark for these 7 values, decreasing value. For part 2, using the same set of axes that you plotted your first graph on, you had to plot a best fit curve for these here. Only 2 marks for this one. So say this was your first curve, that's maybe a bit dramatic, but say that's your first one. The second one should be more sort of like that. That's not a great example. Pretend that looks like an exponential. Bit better, maybe. That would not get me marks for my curve of best fit. So there's 1 mark for your second smooth curve, with your points obviously being correct, 1 for it being steeper than the first curve, and if you messed up and plotted further than 60 seconds, they ignored anything like that. But then they don't always do things like that. Sometimes you'd be penalized for plotting things that didn't actually exist. From your graph, determine the new value of the time constant tau. I've just written in here consistent value. Everyone's will be different, but it's the same thing. You go and you find 37% of the current, see how long that took, and that is your value. Because it doesn't say reliable in this one, you only have to do it once. Then, let me see, for part 4, I think this is the last part, using the equation for capacitors connected in series. So this is an equation we have not taught you yet. The rules for capacitors in series and parallel are basically the opposite of resistors in series and parallel. So if you know those, vice versa them. Determine the value of the capacitance, but again, it told you it. So the total 1 over C total is equal to 1 over C1 plus 1 over C2. You had figured out, what did you figure out? C1 was it? And then yeah, you had to figure out C2, so just substituting your numbers in to the equation correctly there. Okay, so that is the last question. Hopefully that helped. Oh, just on cue, the dog has jumped down. Right, see you soon. Bye.